Hello my friends, and welcome back to the Wow Machine channel. At first glance, it's hard to believe these paper tubes will soon become shotgun shell hulls, strong enough to handle explosive pressure yet made entirely from fiber. The process behind them is a quiet balance between heat, timing, and chemistry. The initial stage uses a 250-pound roll of paper that feeds into high-speed unwinders. Rolls are drawn out, scored, and rewrapped to form consistent layers. Next, the sheet is formed into 12-inch tubes and conveyed to drying ovens until moisture reaches specification. Dried tubes receive lubricant and sizing operations to hit exact inner and outer diameters. Then, they rest in a conditioning room to stabilize. Once conditioned, tubes are cut to 3-inch hull lengths and prepared for impregnation. Hulling involves soaking segments in heated wax under pressure to seal fibers and add rigidity. After a second conditioning phase, the paper hulls proceed to final processing where they are trimmed, packed, and inspected for concentricity and strength. Those inspection gauges don't lie. Every hull must perform under load. Ever thought how a single curve in metal can control water flow? Here's how a pump impeller earns its perfect shape. Few realize how much engineering goes into a part that quietly drives jet thrusters, guiding boats smoothly through the water. It all starts with the preparation of sand molds. Multi-part molding boxes are assembled and filled with a precise mix of sand and clay, giving them the firmness to capture every curve of the impeller's pattern. Once filled, the boxes are flipped to reveal clean cavities where the molten metal will soon flow. One wrong grain size here, and the surface finish could go off. That's how sensitive the process is. The halves of the mold are joined tightly, locking the geometry in place for the casting to come. Even the humidity in the sand can change how the molten bronze behaves once poured. Next, the induction furnace takes center stage. The aluminum-bronze alloy is melted inside a crucible under intense heat, while temperature probes continuously track the molten state. Impurities rise to the surface and are skimmed away to maintain purity. Sometimes the glowing metal almost looks calm, but it hides enormous stored energy. A single pour can reach temperatures high enough to melt through ordinary steel, so precision timing matters here. When ready, the furnace tilts, guiding the liquid metal into the mold through horizontal runners connecting each cavity. As the metal cools, solidification defines the impeller's structure, blades, hub, and core forming in perfect sequence. Once cooled, the sand mold is broken apart to free the rough casting. The fresh impeller, still covered in residue, moves on for finishing. The first glimpse of the solid piece always feels rewarding, like uncovering a hidden shape from Earth. Machining then brings precision to the rough form. Each impeller is clamped and rotated as lathes trim excess material, followed by CNC milling to define the curved blades and balance the weight. Dimensional checks ensure every blade aligns perfectly for high-speed rotation. Some machinists say the impeller almost tells you when it's balanced, not by sound, but by feel through the tool. Finally, the pieces are polished and inspected before packaging. The result: a flawless aluminum-bronze impeller, ready to spin under pressure and channel raw force into smooth propulsion. That's engineering distilled: strength, shape, and motion, captured in metal. A sturdy block of aluminum begins its journey toward becoming a trusted kitchen tool. At Landers, decades of experience merge with refined technique to shape what many homes rely on every day: the pressure cooker. Production opens with high-grade aluminum sheets, which are pressed and cut to precise dimensions for different pot sizes. The forming machines then shape the bodies and lids through deep drawing, giving them their distinctive strength. The rhythmic motion of the press feels almost hypnotic, turning cold metal into something enduring. These presses deliver immense force, and you can almost feel the resilience being forged into every curve. Once shaped, the pieces move to the trimming and polishing stations, where their edges are refined and surfaces smoothed for a clean finish. Next, handles, safety valves, and sealing rings are attached. Each component plays a vital role in maintaining pressure integrity. Some workers even test fit each lid manually before the pressure test, ensuring it locks in place perfectly. The lids are tested to ensure a perfect seal. Finally, branding and quality checks complete the journey before packaging. The result: a pot meant to last decades, passed down through families. Each stage reflects a balance between human skill and mechanical consistency, something that defines Landers' manufacturing legacy. 18 million of these have been made. That's a lot of shared meals and stories, sealed under one lid. Numbers and heat define this craft. Thousands of degrees, tons of pressure, and materials that must endure flight itself. This is where Rolls-Royce engineers build the jet engine's beating heart: the fan blades, fan case, and turbine components that drive power through the skies. Strength here isn't only forged, it's shaped by precision and relentless testing. Every spark, every rotation adds up to decades of refined expertise. The opening step focuses on bonding thin titanium layers into what will become the fan blades. They are arranged in a proprietary pattern before being heated and twisted into aerodynamic form. When inflated with inert gas inside a furnace, the inner walls stretch like elastic steel, forming a hollow yet incredibly strong structure. Even a speck of dust here could ruin hours of work, so preparation has to be spotless. Each inflation takes about 4.5 hours, expanding the blade into its final curve. Once cooled, Every blade is weighed, measured, and rung like a bell to check frequency and balance. Only a perfect set of 20 blades can spin smoothly at thousands of rotations per minute. It's wild to think a few grams can decide how stable a jet engine feels mid-air. Technicians then arrange each blade precisely inside the fan disc. Their harmony ensures minimal vibration during operation. Next comes the making of the fan case, the strong shell that keeps the engine's power safely contained. The first task here is machining down a 5-ton titanium forging to less than 500 kilograms, removing almost 90% of its material. CNC machines run up to 90 hours, cutting walls just 2.5 millimeters thick. All titanium scrap is recovered and recycled. One wrong coordinate could turn a week's work into scrap metal, so everyone stays laser-focused. Meanwhile, welders attach inner guide vanes, titanium pieces shaped and joined by hand under X-ray inspection. The tolerance? Less than a millimeter. Veteran welders still call it a test of steady hands. Some even joke the welds look straighter than their signatures. When the sparks fly, you know something cool's happening. Further into the facility, a new generation of engineers grows single-crystal turbine blades, the true force carriers. They begin as wax patterns, checked under X-rays before any metal casting. Molten alloy flows through a spiral mold, allowing only one crystal to grow upward. The result? A flawless blade capable of withstanding 1700 degrees Celsius, hundreds above its own melting point. Four days of finishing follow, machining, grinding, and inspection down to 1/10 of a hair's width. Blink once and the part's already done. Imagine maintaining that standard across 96 blades per engine. It's an obsession turned into excellence. Each part leaves the factory perfect, built not for show but to survive fire, pressure, and flight itself. Heat, weight, and motion. That's the language of forging at QSC Forge, where solid steel is transformed into rolled rings for turbines, bearings, and heavy machinery. The opening step focuses on heating large steel billets, cut precisely from carbon, alloy, or stainless steel bars. They're placed into gas-fired furnaces that reach beyond 2000 degrees Fahrenheit until the metal glows orange-red. At the ring mill, rollers stretch the metal outward while thinning its wall, gradually expanding it to its required diameter. Operators control both rotation speed and pressure with tight precision. Each adjustment of pressure translates directly into millimeter changes in diameter. That's how sensitive this process is. The hydraulic press communicates in pressure curves, not words. Even a small temperature dip can ruin the balance, so timing is everything. Blink once and the ring's already grown a full size. That much steel moves like clay under the right force. Sensors measure expansion rate and wall thickness continuously. That's how the system avoids internal stress fractures. If a reading drifts even slightly, operators pause the press to correct the curve before it hardens unevenly. Engineers monitor the deformation curve on screens in real time, adjusting torque as needed. They know that once a ring cools below its forging window, no amount of reheat can restore its perfect grain structure. You'd think the job is all machinery, but it's really human intuition guiding the steel. Sometimes a veteran can sense a subtle vibration and know the ring's ready before the numbers even show it. When the final pass ends, the ring's diameter can exceed 3 meters, yet stay within tolerance by fractions of a millimeter. That's why forged rings from here end up in turbines, heavy gearboxes, and jet assemblies worldwide. Once the ring reaches its target dimension, it's reheated for normalization, relieving stress and refining grain structure. The outcome: steel that's lighter, stronger, and ready for engines, turbines, and equipment that never stop moving. Dimensional tests verify every diameter and roundness before shipping. That's how raw force turns into reliability, one forged ring at a time. And once it's forged right, that ring might outlast the machine it serves. Edelbrock's foundry turns molten alloy into the cylinder heads and manifolds, trusted across racing and muscle car culture. Every pour, every mold, carries decades of craftsmanship engineered for endurance. The entire process is about controlling chaos until it behaves like design. Core production marks the foundation of casting. Workers shape sand, mixed with binding resin into solid cores using automated core shooters. The mixture is injected into steel core boxes, then cured under heat to lock dimensions. Each finished core defines the internal passages where coolant or air will later flow. Operators check alignment pins and coating thickness before storage. Next comes the molding line, where silica sand and resin form the outer shape of each casting. Automated machines compress the mixture around a match plate pattern, producing top and bottom halves called cope and drag. Over in the aluminum furnace, raw ingots and recycled scrap melt inside a gas-fired crucible, reaching nearly 350 degrees Fahrenheit. Fluxing agents remove impurities, while temperature sensors feed data into the control console. That leads straight to the pouring line, where the real transformation happens. Ladles filled with glowing aluminum move on overhead carriers, stopping above waiting molds. Each mold receives a timed pour, steady flow rate, exact volume, no splashing. The goal: fill completely without trapping air. Pour too fast, turbulence forms defects. Too slow, the mold chills unevenly. Once cooled, the line proceeds to mold punch-out. Machines separate sand from metal, using vibration and impact. The core sand collapses easily thanks to heat degradation, while the outer mold breaks apart under hammer presses. Conveyor belts carry hot castings away for inspection. Next is deburring and cleanup. Here, grinders, rotary brushes, and CNC trimming tools remove flash lines, sharp edges, and excess metal. Robots handle repetitive grinding, but technicians fine-tune contours around the intake and exhaust ports. The surface finish affects not just looks, but also thermal efficiency. Castings are washed in high-pressure cabinets, then dried with filtered air. Dimensional checks confirm that every port and bolt hole meets spec. A single burr could mean a leak under combustion, not something you'd want at 6,000 RPM. Even the smallest leftover ridge can alter airflow dynamics inside the cylinder head. This step feels like sculpting speed itself, removing imperfections until only performance remains. Every clean surface means smoother combustion and higher output when the engine fires. Finally, the cylinder head production line turns rough castings into high-performance parts. CNC machining centers cut precision valve seats, chambers, and bolt patterns. Coolant jets control temperature while cutting tools follow programmed coordinates. Workers verify alignment with coordinate measuring machines before assembly. Valve guides, seats, and inserts are pressed in, followed by surfacing for gasket fit. The completed heads are deburred again, inspected for porosity, and given serial numbers for tracking. Hard to imagine each piece once started as glowing liquid metal. After quality approval, they're packed, labeled, and sent to the assembly floor, ready to handle combustion, boost, and pressure for years of hard driving. Every casting tells the story of heat, skill, and persistence. What emerges from Edelbrock's foundry isn't just aluminum, it's reliability forged under control. And somewhere in that noise and glow, you understand why old-school foundry work still matters.